Welcome everybody to this Expert Midas webinar. This is Ruben Arias and I'm going to show you some technical details to model a long high-speed railway bridge designed by Ingenieria, paying attention on dynamic analysis. This presentation is organized as follows. First part, the bridge, an introduction to main features of this project, location, dimension, and some other topics. The second part, the dynamic analysis. We will go over dynamic requirements and how to define time functions and interesting proposals for design strategies. The third part is the conclusions. Let's start introducing the project and its main features in Genesis and a short description for construction stages. In foundations, we will see one of the keys to design for dynamic analysis by adopting a special strategy for foundations. And of course, the loads. Well, Hernani Viaduct is located in a strategic point between Spain and France, just in a traditional communication corridor to the heart of Europe. This special corridor will support a high-speed railway to connect Madrid, the Spain capital, to the north of the country and France. Hernani is a small village close to the coast where there is a confluence of highways, railway, and a river. This physical feature of the site increased the initial difficulty to cross the village by a high-speed railway, so a long bridge was proposed as a solution to overcome some such difficulties. This picture partially shows the viaduct crossing the river, the highway, and the existing railway. This is a 1,400 meter long viaduct made by continuous deck without using any intermediate expansion joint. And this feature makes this project really special. Most of the spans are about 25 meter long, but when crossing the river at this point, the spans are longer, between 60 and 90 meters. And a steel lattice girder are used to support the deck at this point. One detail is this steel structure is that its section is filled with concrete. As a result, different sections are used for medium and long spans. As seen in the picture, the deck is 14 meters long to support two railway tracks in a continuous voided concrete slab, which it rests on two piers at each span. This is the span for medium, and this is the long span with steel arcs. The solution for foundation is different for medium span and long as well. In this picture, pile caps are used, but the difference between them are so clear. Since the site is close to a river, geotechnics was a really challenge to ensure a reliable support to this large bridge over a soft sedimentary soil. As a reference, pile caps are about 2 meters height and the piles more than 45 meters. This is a picture about one construction stage. As seen in the picture, foundation is not modeled by using regular elements such as beams or whatever. Due to the big size of this bridge and the huge number of nodes and elements required, foundations, piles and abutments have been modeled rigorously but using an alternative technique, replacing an equivalent boundary condition. This is another picture which explains this approach. Foundations are modeled as general spring supports. From the point of view of the general structure, the result is the same. From the point of view of the designer, this means less time to run models, lower risks of errors, simpler models to check. In a nutshell, a simple way to increase the productivity by using meta-stable. As a consequence, a separate model is needed to calculate its foundation, mechanical features, and its corresponding equivalent general spring support. This is an example of twin monopiles connected by a branching beam in order to enhance their behavior. In this case, pile cap is not needed due to show features, but the pile is 45 meters height. As shown in the right, the model for this kind of foundation is an isolated pile using linear spring supports which have their own constant each one, according to general geotechnical report. For vertical reaction, only compression spring is used. The following model is needed in a few of medium spans and the long spans. A pile cap is modeled by using a master node and 4 elastic links to their corresponding head piles. Point spring supports are applied to nodes to simulate the solid behavior as seen in the previous slide. For dynamic calculation, it's especially important to model the real foundation stiffness, since dynamic behavior is very sensitive to this feature. Foundations cannot be considered as fixes anyway. To calculate an equivalent general spring support, the following process was applied to each foundation model. First, applying unitary displacement as static load cases. So we get 6 static load cases for each movement. Second, extracting all reactions for each load case. Some of them can be ignored if they are small enough. Third, define general spring matrix by using the previous results. This is a very simple way to substitute any partial structure model, in this case foundations, by a single general spring support. That means a save of more than 100 extra elements and 100 extra boundary conditions for each span. That is about 6,000 elements and boundary conditions. For dynamic analysis, the most important load, apart from self-weight, of course, is the traffic load. It is mandatory according to the code for this type of structure to consider HSLM trains. That is a collection of 10 different trains which can go through the bridge at different speeds. There are a variety of different number of coaches, lengths, and load per axle. There are, of course, many other types of forces, such as horizontal, such as centrifugal, wind, climate actions, accidental actions, and in this case it was need a special study of fluids, but the most important is the traffic. Well, in this part, the dynamic analysis, we will discuss about the following topics. A small introduction about impact factor for real trains, according to your code. The number of considered train speeds. Small explanation of how to make time history functions from a simple signal to a more complex for real trains. Finally, we will see how to implement on Midas Cybele all dynamic information by using the dynamic nodal forces and how to define dynamic load cases. For real trains, there are some reasons to perform a dynamic analysis. First of all, to avoid reaching a maximum deck acceleration as a safety limit state for the traffic. The other reason is for calculate the impact factor. Due to the movement, there is an amplification of static effects for displacements and efforts. And although there are analytical expressions to calculate impact factor, they cannot be applied for this project due to its complexity and size. So, safety and impact factor are the main reason to carry out dynamic analysis. The following picture shows the acceleration of a deck point in time. These simple graphs and few more are the final result of a very complex and comprehensive work that we will discuss on the following slides. First of all is considering the speed. According to code, we must consider from 20 kilometers per hour to 1.2 times the design speed. This means considering up to 200 kilometers per hour. For modeling, we can take an incremental value of 20 kilometers per hour. That is a sequence of 20, 40, 60, 80, up to 200 kilometers per hour, being altogether 10 different speeds. Keeping in mind that HSLM trains are 10 different traffic load cases, this means 10 trains and 10 speeds equals to 100 different load cases. In our case, 10 different models are considered for each speed level in order to manage a simple set of models which they include 10 different cases, each one for one of the 10 trains. Time history functions. In the pictures, we can see typical times functions related with vertical loads and its effect on a deck element. The first image in the left top shows how to compound two simple functions, one in blue and the other in purple, which represent two axle loads. The difference between them depend on the distance and on the speed. By adding these two functions or compound, we get the function in green. That means that an initial 100 kilonewton load per axle gets up to 150 kilonewton as compound load. If the element of the deck is shorter than the distance between axles, the blue and the purple functions will be separated enough to make green function reach only 100 kilonewton as maximum value. The other picture shows this effect as a so-safe functions in this way when elements are short enough. This kind of function can be done with data generator tool in Viaduct, but you will need to edit them to indicate a different arrival time for each node due to its position on the deck. So the number of required functions is increased a lot. The other detail is defining a good dynamic analysis case. For this project, we will need transient and direct integration options. The end time depends on the speed and the length of the deck and the train. But the key is the time increment. In order to check a time function, it is necessary to take 8 points, as shown in the picture. That is dividing by 8 the main period. The period is the time one axle takes to cross an element, and the shorter element, the shorter time increment. For example, for a one element and 180 km per hour, the time increment should be less than 2.5 nanoseconds. That means thousands of steps. For the sample in the picture, there are one load case for each train, that is, time history load cases. There are more than 4,000 functions, half for forces and half for moments. The reason is that there are different element sizes due to the complexity of the model. There are almost 16,000 dynamic nodal loads, resulting to add different arrival times for each node. This amount of information needs to be automated by, in this case, making macros or simple programs to write MCT files. The best solution for civil to manage a big amount of data entry. As a conclusion, to carry out big dynamic analysis projects in a reasonable time, one needs to apply model simplification, such as the use of general spring supports, which are inaccurate equivalent foundations. Apart from this, large bridges for dynamic analysis need to define thousands of dynamic loads. This point can be carried out by using MCT files and a little of programming. I want to thank a lot to the company Ingenieria for this wonderful example of how to design a long high-speed railway bridge. And thank you very much for your attention.